Vehicle casualties is a serious matter, and the aim of this project is to find some trends in vehicle casualties over the years. The project can be used to help give an idea of what actions need to be taken, or whether action does need to be taken to help reduce road casualties. The data that we'll be using is about the vehicle user casualties in the UK from 1979 to 2008. It has 10 variables, 9 independent, which are the first 9 variables you see in the PowerPoint slide, and the last one, which is the licensed vehicle casualties, is the 10th independent variable. So the first objective is to predict the number of car user casualties in 2009 using linear regression. For this analysis, I decided to use Microsoft Excel because it has a lot of built-in functions to simplify things and save time. Here's a quick overview of the correlation table. As you can see, a stronger red color means a stronger negative correlation, and a stronger green color gives a more stronger positive correlation. And you can already see that there are some significant correlations within the variables. So for our first objective, which is predicting the car user casualties, the response in a regression model is the number of car user casualties. The constant in the predictor is the predictable variables, and the error is what you get when you take away the observed with the predicted. Essentially, in a regression line equation, the independent variable x will be the value of the car user casualties, and the dependent variable, which is y, will be the year. Actually, the other way around. After experimenting with Microsoft Excel's trend function, it was obvious that the best type of polynomial regression for this object was full-order polynomial regression. Any more than that would be considered overfitting the data. Over the next few slides, I will talk about the certain techniques I used to determine how accurate and reliable my analysis was. So first, the residual error. The error is equal to the observed value minus the expected value. The residual error estimates true error in the same way the regression line coefficient are estimates of the true population's coefficient. In the real world, error cannot be predicted. It is the same way you cannot predict a 6-sided die since it gives random values. In the same way, the plot of the residual errors should be random, and a good plot meets the following requirements, as shown in the PowerPoint. The image above shows the residual plot of the regression model, which mostly meets the requirements. However, there are some areas it can improve on, and to do this, the data would need to be transformed. The next technique I use is the R-squared value. The R-squared value determines how well the regression model fits with the observed data plots. The smaller the difference between regression model and the observed data plot, the better. On the other hand, a limitation of R-squared is that it only increases, so the more variables you add, whether useless or useful, so the better solution for my case, which uses multiple variables, would be to use the adjusted R-squared. Looking at the equation below, the adjusted R-squared is better because it takes into account whether you add useful or useless variables, and it gives a new R-squared. In conclusion, here's the regression model of all my analysis. The predicted number of car casualties is 130,000, but the actual number, looking online in Datagov.uk, is 143,400, which isn't too off. There is approximately 15,400, which is just over my standard error. In terms of percentage, it's just very small. So having completed this objective, I can say that the outcome of this analysis or the regression model is quite accurate and reliable, but however, realistically speaking, this will only be reliable for maybe a few years. Finally, as an evaluation for this project, I've realized there are actually quite a lot of factors that need to be considered for this model to be more reliable and to be further improved.